Chapter 9 Matrices, Section 9.3, the inverse of a matrix. We'll now see how to find the inverse of a matrix and then how to use the inverse to solve a system of linear equations. To be able to find the inverse of a matrix, we have to find something first called the determinant of a matrix. A determinant is a number that's associated only with square matrices. So first of all, we have to have a square matrix. The determinant of a square matrix A can be denoted, and that's read the determinant of A. It looks like absolute value of A. It's the same symbols that's used for absolute value, but it's just read as the determinant of A. For a 2 by 2 matrix, the determinant is computed as follows. So given the 2 by 2 matrix A with entries A, B, C, and D, the determinant of A is A times D minus B times C. To compute the determinant, notice that what you look at are the entries in the main diagonal and the off diagonal. It's sort of like a cross product, you might say, multiplying A and D, then C and B, and then taking the difference. So it's actually quite an easy computation. It's just a difference of two products. So let's find the determinant for a couple of specific matrices in example 1. We have the 2 by 2 matrix shown in example 1a, and let's just consider this the product of the entries in the two diagonals. So the determinant of A would be computed by first multiplying 4 and negative 1, and then 2 and 3, and then taking the difference. So in this case, that's going to be negative 4 minus 6, or negative 10. So the determinant of A is the number negative 10. Let's look at matrix B. Okay, again, we'll do these two multiplications. So the determinant of B is the product of negative 3 and 3. And then we need to take the product of negative 1 and 9 and then subtract. So you have to be careful with your signs here. Because it is a subtraction, and you sometimes have to subtract negative numbers. So we would have negative 9 minus negative 9, which is, of course, actually negative 9 plus 9. So here the determinant is 0. So this shows us a simple method for finding the determinant of a 2 by 2 matrix. These are the only types of determinants that we will deal with. There are methods for finding determinants for larger matrices. The matrices have to be square, but they can have an order greater than 2. So for order 3 and higher, there's a more involved process for finding the determinant, and so we will not go into that, but I will tell you that a standard graphing calculator can be used to find such determinants if for some reason you need to compute one. We're now ready to define the inverse of a matrix. So let A be a square matrix of order n with non-zero determinant. So notice two conditions. We must be dealing with a square matrix, and the determinant must not be equal to 0. The inverse of A, denoted, and it looks like A to the negative 1 power, but it's simply read as A inverse. That negative 1 is not an exponent in this case. It's merely a symbol denoting the inverse of the matrix A. It is the same symbol, of course, we use for reciprocal, but here it's not a reciprocal. So the inverse of A is the matrix with the property that A times A inverse, A times A inverse, or A inverse times A, so we can multiply in either order, is the order n identity matrix, IN. So if we multiply a matrix by its inverse, we get the identity matrix. If the determinant of A is equal to 0, then A does not have an inverse. So we must have a non-zero determinant to be able to find the inverse of a square matrix. Example 2 asks us to show that the inverse of a given matrix A is, as shown, A inverse -3, -4, 1, 1. All we have to do to show that two matrices are inverses is to multiply them. So we take A times A inverse, and when we do the multiplication, just write the matrices side by side. And since they're both square of the same order, they can definitely be multiplied. The product will be a 2 by 2 matrix. And I will show you some of the computations involved just to review the method of matrix multiplication. 4 entries. First entry is found by multiplying the entries in the first row of matrix A with the entries in the first column of the matrix A inverse. So, and this is done as a dot product, and I would just refer you to the previous notes for the specific method. But here are the numbers we would obtain. 1 times -3 is -3. 4 times 1 is 4, and we would add. Then we would take the first row of A with the second column of A inverse. That would be 1 times -3. Excuse me, I have the wrong number there, just a moment. Let's try that again. It would be 1 times -4 plus 4 times 1. So -4 plus 4. Then the first entry in the second row would be the second row of A with the first column of A inverse. That would be -1 times -3 is 3, plus -3 times 1 is -3. And then last entry would be second row of A with second column of A inverse. -1 times -4 is 4, plus -3 times 1 is -3. What we then obtain, adding, we get 1, 0, 0, 1. In other words, we get the order 2 identity matrix. So we do get the desired result, showing that A and this other matrix labeled A inverse are indeed inverses of each other. So you could actually, you can say that they're inverses of each other. A is the inverse of A inverse as well. And we could also show that if we multiplied in the opposite order, we'd obtain the same result. We won't go through that, but we could verify that. So this is a situation, if you multiply a square matrix by its inverse, you get the same result regardless of the order of multiplication, which is generally not true for matrix multiplication, as we saw in the previous section. The order usually does make a difference, but here it doesn't. So next, how would we actually find the inverse of a 2 by 2 matrix? Well, there's a little formula, so to speak, that you can use. For larger matrices, it's a little bit more involved, but again, we will focus on the 2 by 2 case, which is rather simple, actually. So if you're given the 2 by 2 matrix ABCD, the inverse of A is 1 over the determinant of A. And then notice a couple of things. For the entries in the main diagonal, they get interchanged. D goes to where A was, and A goes to where D was. For the entries in the off diagonal, they don't get interchanged, but we do take their opposite. So we have minus C and minus B. So those stay where they are, but we take their opposite. So there's two things that happen. The entries in the main diagonal switch. The entries in the other diagonal, we take their opposite, but they don't switch. And then we multiply, and it's a scalar multiplication, since the determinant of A is just a number. We multiply by the reciprocal of the determinant of A. And since we are dividing by the determinant of A, we must have a non-zero determinant, as mentioned previously. Otherwise, the matrix does not have an inverse. So let's apply this to the matrix A from the previous example and show that using this formula we do obtain the inverse that was given in that example, in example 2. First of all, we have to compute the determinant of A, and for that we use A in its original form. And we're going to do those two products. So the determinant of A is 1 times negative 3 minus negative 1 times 4. That is, it's negative 3 minus negative 4, which will be plus 4, which turns out to just be equal to 1. All right, now let's apply our formula from above. The determinant is not equal to 0, so we can definitely find the inverse. So it'd be 1 over the determinant of A, which is just 1 in this case. Okay, we're going to switch the positions of the two entries I just circled. So that would be putting negative 3 here, positive 1 here. Then for the other two entries, we're not going to change the position, but we are going to take the opposite. Negative 4 and positive 1. Now, since we are doing a scalar multiplication by 1 over 1 is just 1, there's really nothing else to do. We just write down the result as negative 3, negative 4, 1, 1. And if you go back and look at the matrix A inverse in example 2, that's exactly the inverse that we were using. So we do know that when we multiply this matrix with A, we do get the 2 by 2 identity matrix. So as you can see, it's a fairly simple computation to find the inverse of a 2 by 2 matrix. Let's now find inverses for a couple of additional 2 by 2 matrices, just to go through the method a couple more times. So we have the 2 by 2 matrix B that's shown in example 4a. We first need the determinant of B. Okay, so we're going to just do these two multiplications. 3 times negative 1 minus 2 times 0. That's negative 3 minus 0, so that's just negative 3. So since the determinant of B is non-zero, we can find the inverse. So B inverse is 1 over the determinant of B, which is negative 3. And then remember what we're going to do. With the entries in the main diagonal, we're going to switch them around, negative 1 and 3. With the entries in the off diagonal, we're going to take their opposites. But we're going to leave them otherwise where they are. So the opposite of 0 is still 0. The opposite of 2 is negative 2. And then we just try to simplify it. We're going to multiply each entry. This is a scalar multiplication inside the matrix by negative 1/3. So negative 1 times negative 1/3 is positive 1/3. Negative 1/3 times 0 is just 0. Negative 1/3 times negative 2 is positive 2/3. And negative 1/3 times 3 is negative 1. So this is the inverse of B. Notice we obtained some fractions. That is not unusual when you're finding an inverse because of the fact that we're multiplying by the reciprocal of the determinant. So don't be surprised if you get some fractions when you